Okay, so we'll get started now. So, welcome to the latest in the series of Spaceport Frontiers lectures. You would have noticed that I'm not David Alexander. He is doing important things somewhere else and has asked me to step in for the evening. My name is Steve Bradshaw. I'm one of the professors in the Physics and Astronomy department. So it's my pleasure to welcome you all this evening, and actually my pleasure as well to welcome a group of people who have come from quite far afield. We have a group of high school students from Scotland in the audience today, the Scottish Spaceport. Give everyone a wave. So these students have basically been chosen in a competition to come to Houston and spend some time here getting immersed in sort of space-related activities. And so we're delighted to have you here and hope that you're having a great time. So now it gives me great pleasure to introduce our speaker this evening, and I've been told to be brief. So all I'm going to say is that it is fantastic to welcome Dr. Jim Green this evening. He has had a very long and distinguished career at NASA, which you can read about online if you so desire. He is the Director of Planetary Science at NASA headquarters at the moment, and he is going to speak to us this evening about using shadows to shed new light, which I'm sure he will shed new light on for us now. So, welcome, Dr. Green.
Thank you very much, Stephen. It's really a delight to be here for the Frontier Lecture Series. And tonight, it's all about how we use shadows to really do some new and exciting science. And the importance they play in that science will be unmistakable by the end of this little lecture. What's critical to remember is that what are we talking about in terms of shadows? A bright light between you and that light, something moves in front of it, creates a shadow. And so we have actually a number of names for these things: eclipses, occultations, transits. And over the last year, those three techniques, producing shadows of one object moving in front of another, have been used in an enormous number of ways, all the way from the spectacular eclipse here in America to finding new planets around other stars. So tonight I'm going to talk about shadows in several areas. One, we'll concentrate a little bit on the great solar eclipse of 2017 that happened in August. Then we'll also talk about how shadows are used in science in our solar system. And I'll give you a couple current examples that occurred over this last year. And then eclipses in other solar systems and how we're using that information to interpret those observations. Now, in many cases, these shadows lead us to a set of observations that we then follow up and gain more insight. And so, in many ways, it's just the start of some of the science that we're doing. Now, I hope everyone had the opportunity to participate in some way in the Great American Eclipse. Perhaps even the other students that came from such a long way, at least have heard about it. But this was an enormous event. On August 21st, we had a total solar eclipse that cut across the country. 14 states were involved. 154 million Americans, actually adults, watched the eclipse. 20 million, it's believed, traveled to the eclipse region to be able to watch the eclipse. And 61 million Americans, adults, viewed the eclipse by other means, either on TV or over the internet. And that results in about 88% of the adult population of America had some sort of eclipse experience. It was just such a phenomenal opportunity for Americans to really participate in a really great event. Well, this is not an unusual event. It happens all the time. you know, on the order of not necessarily every month, but quite frequent. You sometimes have to travel great distances to be able to see one. And of course, the next one in America is in 2024, in the April timeframe. Now, what we did in this eclipse, even though eclipses are actually fairly common, is we actually did a lot of really new and exciting science. And it's you know, sometimes hard to imagine, haven't we done everything that we need to do in eclipses? But we always find new and exciting ways to do some new science. So here's one of the first observations that NASA did. NASA actually had a plane off the coast of Oregon observing during the eclipse time period. And indeed, you can see the eclipse in the corner. And it really tested a variety of instruments, looking at faint light and looking at the lower corona. Others were actually looking down at the shadow. This is a speed-up version of the shadow racing across the clouds as actually the plane was in motion and making the observations, testing those instruments. And it's a pretty spectacular view from that perspective. Another set of experiments that were done were actually looking at the sun, looking at what the corona looks like. This is the extended atmosphere of the sun during this occultation, because we can actually see that in great detail. This is actually an image from SOHO, for which we actually have coronagraph, it's called, that blots out the sunlight and then looks at scattered light all the way around the sun, and you can see some of these really great features that participate in coronal mass ejections and in a variety of other events that we know so well. The problem is, this is some of the best techniques we've ever done from space, and yet we really are missing an enormous amount about the corona. And so here is actually an eclipse picture that fills that area in that some of our space observations don't have the opportunity to see. So during the eclipse, it enables us for the very first time to be able to look at the lower corona, and look at the structure of these hot gases that are in the lower atmosphere of the sun, that eventually, some of which are trapped on magnetic fields, some of which are participating in the outgassing of the sun that we call the solar wind. Reconnection events occur, and huge pieces of the atmosphere blow off and go into space. And so understanding some of these coronal dynamics are extremely important. So one of the sets of activities that these scientists did, indeed, was start with the coronal emissions that we can see from spacecraft, and then begin to model that in terms of its magnetic field structure. And then, because the sun spins on its axis, try to predict what kind of brightness distribution we would see, and then during the eclipse, look at the difference between what was predicted from our massive computer models to then what we actually observe. And so here's the comparison. And for the plasma physicists in the crowd, the real set of observations are in the lower panel. And so actually we're getting really pretty good in terms of understanding a lot of the dynamics of the sun, and this clearly demonstrates we're making great progress in this area. So solar physics had enormous benefit in terms of what we could do during these eclipses. So in the shadow of the moon, we could actually look at that lower corona and validate a lot of our models that we couldn't have done otherwise. But there was other activities that we did. Along the eclipse path, there were 57 balloons that were launched. These balloons went up to altitudes greater than 100,000 feet. That's above 20 kilometers. And they were designed to have basically an imager on it, a GoPro-like system that'll be able to look down and, like the plane observation that I showed you, see the shadow sweep across the country. But this also provided us an opportunity to do an experiment in planetary protection. What we wanted to do was put on board each of these balloons, or as many of them as we could, and it turns out instead of all 57, we got the experiment on 39 balloons. Here they are arrayed across the eclipse path. And they were launched with 34 teams in 10 states. All these balloons went up to altitudes of 100,000 feet and greater, and we were asking two primary questions. We put pretty hardy bacteria on little strips, and we wanted to see if that bacteria, as it went up to those altitudes, were to survive. So, during a full solar eclipse, is the stratosphere a good Mars analog? At 20 kilometers, what is the temperature and pressure, and how does that compare to Mars? And then what kind of bacteria would we use? So the answer to the first question is, yeah, it really turns out to be a great environment. So you can see in the table, the pressure at altitude is very much like the Mars pressure that Curiosity observes. Also, the UV broken up in these three bands matches really pretty well, far better than what's on the Earth in all of these areas. The ionizing radiation is a little different, although we have a magnetic field that does indeed affect the environment of cosmic rays and high energy particles that can get into our atmosphere. And so that was considerably different than what it is on Mars. But then the temperature range is really right on again, where we have very low temperatures just like the surface of Mars. So the answer to the question is, if these bacteria, human biobacteria, go to high altitudes, would they survive in a Mars-like environment? And so here's what we found out so far. The bacteria coupons that we created are about like a credit card. We put them on two of these little metal panels. One we kept down on the ground as a control, another one that we launched individually in each of the balloons. Bacteria is Pentobacilla xerothermoduron, and it's really pretty hardy. We found these outside of clean rooms at Kennedy Space Center. And you can see where we position these balloons, position these coupons on the gondola, and then we would launch these. Now these are elastic, latex-like balloons under pressure, helium pressure. As they go up, pressure around them decreases, they get very large, but they're able to expand to a very large size, and then at about 110, 115,000 feet, they break, come down, and indeed the gondola also enables us to geolocate them. So in the upper panel, what you see is the actual track of three of these bio-coupon balloons, fitted balloons. And these three stay above 20 kilometers, which is our threshold to get above the ozone. This is where the ultraviolet light matches mostly of what Mars is like, for at least 1 hour, and in the other case, almost 2 hours in itself. So we've recovered about 26 of these, and we're in the process of analyzing them, and they're going to help tell us, indeed, if this kind of bacteria, which is probably on the Curiosity rover, is surviving on Mars or not. Okay? And we'll actually have some observations to be able to determine that. If the environment is such that it kills this type of bacteria extensively, we may be able to have the arguments that we need to be able to say we can take Curiosity and move it to locations where there might be special regions and we might be able to look for life. We don't know that we can do that, but this is the kind of experiment that allows us to make the next set of observations and help us make that kind of determination. So now let's talk about using the eclipses to explore our solar system. And I want to start out with going to Saturn. Okay? Now that might be an unusual place to start out talking about shadows, but we had a situation for which we found with Cassini two extremely special places. These are moons at Saturn. One's Titan and the other's Enceladus. Titan is the only body besides the Earth that has liquid on its surface. And it's not water, it's methane. And a liquid, like water, is so critical for life because of the ability to aid in metabolism, being able to eat things, break apart, get the energy, and then eliminate waste through that. And so perhaps a liquid like liquid methane on another world could serve that purpose for a different type of life that we have maybe no idea of how it's based or any aspects of it. So if there's life like we've never seen, like us, somewhere in the solar system, going to Titan is our first best choice to do that. We also ran into a moon like Enceladus. This is actually a fairly small moon, about 250 kilometers in size. And in the four huge cracks in its southern hemisphere, geysers of water are pouring out of this particular moon. We've flown through these geysers, and we've made a number of measurements. There's organic material there. There's plenty of indication that it's being heated by hydrothermal vents that are in the ocean, the bottom of the ocean in Enceladus, and we now believe that Enceladus, underneath this icy crust, has a global ocean. And so it's potentially a wonderful place that may actually harbor life. And now we have a spacecraft called Cassini that wasn't really designed to be, have the ability to protect any life that it might go to, because on it is human life. There's a human bioburden on that particular spacecraft that we didn't clean off. We had no idea that we would need to do that. And so this moved us in the direction of, we need to protect these places. We need to go back and interrogate them, but we will not infect them with human life or even have that opportunity. So we need to figure out how to get rid of the spacecraft. This is the orbit of Cassini over about a 10-year period. It stayed in the Saturn area for 13 years. And we used Titan as swing-bys and created huge changes in its orbit. But we recognized what we had to do to ditch the spacecraft, and that is to get rid of it in this environment, since we didn't have enough fuel to leave the Saturn environment, actually was to plunge it into the atmosphere. And it's done in 2 steps. And that's what these 2 orbits look like. And they're tricky orbits. For instance, in calculating how we would do that, our orbit dynamicist said, okay, the first thing we do is we get a gravity assist from Titan, and then that gravity assist allows us to get really close to the rings. And we want to fly just outside the F ring. Now, we want to avoid rings for the simple reason that, a grain of sand hitting our spacecraft, which sometimes is moving at 10 kilometers per second or greater in these particular areas, in the wrong place, would really take the spacecraft out. So we really had to say, okay, we want to look for regions where the spacecraft would be safe. And then on another swing by a Titan, after about 20 what we call F-ring orbits, these are those outside the last ring, this F-ring, then we can jump inside the rings. And jumping inside the rings then would ensure that we could put it on an orbit and a trajectory that would then ditch the spacecraft. And so that's a total of 42 orbits, 22 inside below the rings, just above the atmosphere, in those outside the F-ring. So, how did we figure out these orbits? Because we needed an eclipse to do so. Here is one of the first eclipses that we took of Saturn moving in front of the sun with Cassini looking back. So all these observations are done on the night side of the planet Saturn. And you see the rings. The rings are because the light from the sun is reflecting on the atmosphere, which reflects on the rings, which reflects back on the atmosphere, and illuminates this back area. This is our first major attempt at doing that. And of course, the area of interest, this particular area, then we could concentrate on understanding the very small particles in this particular area to determine the safe trajectories. And when we blew that up, here's what we discovered. We discovered 2 new rings. Okay? And one of them, the Janus Epimetheus ring, which is below the G ring, but above the F ring, is right in the wrong place. Okay? This is an area where this material we'd have to plow through, and we'd lose the spacecraft. So we had to be very judicious about that, and we're also quite interested in what's happening just above the atmosphere, because that's an area we were also going to fly. And so these occultations were really important. These eclipses, rather, were really important in helping us determine how we were going to do that. So here's the set of observations. We laid out the rings, and so you have the distance from the center of the planet over a period of time, and each of these dots are really where the Cassini spacecraft would go right through the screen, perpendicular to the screen above us. And as you can see, that red line is the peak of the dust area of the Janus Epimetheus ring. Okay? And then below that, we found that the extended F ring also had a significant amount of dust. And so that enabled us then to pick the locations between that carefully selected location to fly our spacecraft through. And then, of course, when you look at the lower curve, the last set of blue dots off to the right in the very end is certainly what we believed was well below the D ring, that first ring that you have to worry about. And we were just going to have to take our chances. Now, it didn't look like much was going on there. So that may mean little bitty dust, but not very dense, very sparse. That would be good. Or it could be some pretty big stuff, but also very less dense and not observable. So we were going to have to take our chances with that. So once we decided to do that, we began to execute that. What did we learn? Well, we learned a whole series of new sciences because of these orbits. We were able to look at these moons, these very small moons that are in and around the outer parts of the rings of Saturn. And these moons, which are shown here, we got tremendous close-ups of these. We could actually see ring material accreting to these bodies. As you can see, the pan looks like a piece of ravioli with it, and it's right in an area in the A ring where the material has to cross. Pan is going to pick it up, and it ends up producing this belly band. Atlas 2 is quite an accumulator of ring material. So we had really some tremendous observations looking at the dynamics of the rings and trying to understand what's happening in this particular area. And so that was pretty spectacular. We also had absolutely spectacular views of the northern and southern hemisphere of Saturn. And in the northern hemisphere, we've known about what's called the hexagon for a considerable length of time. There was a hint of it even with the Voyagers as they flew by. But this really gave us an opportunity to take a really good look at the hexagon and watch it evolve over time. Now, the size of this hexagon is about 2 Earth diameters. You could think of 2 huge Earths. And this hexagon is actually what we believe is a jet stream. So this is a jet stream that's set up. Its shape, obviously, is a hexagon. It's a very stable shape. And in many ways, we're struggling with trying to understand this. And it's requiring some really sophisticated magnetohydrodynamic modeling to be able to try to predict the shape. What's also pretty spectacular is right over the pole, which is this enormous hurricane. And you can see, based on the sunlight, that these clouds raise well above the normal cloud deck, and we can actually watch and see the dynamics that are going on here. And so a lot of Saturn atmospheric circulation patterns are being observed and really noted. And it's really been pretty spectacular. Now, we got pretty good at these kind of eclipses, and this one, as you can see, is so much different than the previous one. The first one I showed you was indeed the very first time we did that. This one we did just for the fun of it, the inspiration of it. It has a wonderful configuration of the planets, Mars, Venus, and if you look, they're each little bitty dots that are sitting there that are so far away. Saturn itself is at 10 astronomical units away from the Sun, where the Earth is at 1 astronomical unit. Okay, Mars is like 1.5 astronomical unit. And when we spent time doing this long-term exposure, we can actually see the Earth and the Moon. So it's really a spectacular set of observations. So this set us up for the finale. We were confident that we could fly through these areas. As we flew through the area below the rings, we discovered only a few very small particles, and then that enabled us to make the 22 trajectories through that. The two sets of orbits orbiting outside the rings enabled us to get the mass of the planet plus the rings. And when we took the 22 orbits below the rings, just above the atmosphere, we can get the mass of the planet. And therefore, when we subtract the two, we can get the mass of the rings. And the current theories are, if the rings are fairly massive, like some of these small moons all ground up and contributing to the rings, then they may be very old. If there's not a lot of mass in the rings, they may be very young. And we're in the process of completing that analysis, but it looks like the rings are pretty old. So here is the last image that Cassini took. It's actually a mosaic. It's several images that are stitched together. It's almost in eclipse, and it goes right over the polar cap and then enters the atmosphere at 10 degrees, as you saw in that earlier simulation. So once again, this whole mission was facilitated in its end by using the eclipse technique to understand what the possibilities are for us to be able to make new science happen and do it in a way that we were in control. Another spacecraft, New Horizons, flew by Pluto a couple years ago. Now, before it did that, we actually had a number of occultations. And this is where Pluto moves in front of us and a star, okay, and blots out the light of the star. So in the shadow of that star, reaching all the way back to Earth, you can see in this lower panel, here's the distant star off to the right, and there's Pluto's shadow. And then you can see in the lower left, you can see the size of what that shadow would be. And then it's sweeping across the Earth at about 53,000 miles per hour. And as you can see, there's not much land in the area. In fact, the center of it was completely over water. The only way we could do that is through observations with a plane. SOFIA is the perfect tool to use. It's got, it's a 747 with a hole in the side and a beautiful telescope that allows us to stare at the star and watch Pluto move in front of it and allow us to analyze then the shadow. Here's the observations from that flight in 2011. And the blue line is actually what we would expect to see if Pluto was just a hard rock. Okay? So what would happen is the light would be immediately blotted, would go straight down, and then come to what we call the noise level of the instrument, go straight up, and then back at a steady level as we observe the star. But as you can see, that is not what happened. The actual light began to dim well before the star actually was being occulted by the surface. And so that's because it has an atmosphere. And then at the very center, that star is illuminating the entire atmosphere, producing a beautiful little ring, giving us a little additional flash because the atmosphere is bending those waves just in the right way to come to Earth. And that gives us a peak. This enabled us really to study the atmosphere of Pluto before New Horizons got there, and allowed us then the process of being able to plan on how to observe it. Now, of course, here's the beautiful Pluto. This is actually in enhanced light, but pretty close to visible. What we see are some unbelievable different regions. You know, the heart region is actually nitrogen ice, methane ice, and carbon monoxide ice. We also see methane snows in the northern hemisphere. And now there's a region of dark red material streaking over part of it that are called tholins. These are complex compounds that are made up of carbon and hydrogen rearranged, not like methane, but more like ethylene and acetane and a number of other things. And it's because of the breakup of the material that we see, and that must be occurring in the atmosphere. Well, New Horizons did what we expected it to do, and indeed, knowing that there was an atmosphere there, its trajectory was planned such that another eclipse would occur, with Pluto moving in front of our own sun, lighting up that atmosphere, and indeed, we could see that eclipse, and that was very important because we could also target certain areas and look at the atmosphere in great detail, and we saw enormous amount of structure in that atmosphere. And as we look at the atmospheric components and understand what happens to them over time, they in reality we recognize there's what we call methane cycle. And that methane is in the atmosphere. It gets broken up by ultraviolet light. It also gets broken up by the solar wind, since Pluto doesn't have a magnetic field. It creates acetylene and ethylene, and then that also recombines into much heavier molecules that then cannot be sustained in the atmosphere, and they actually snow out and fall on the ground, and they are red. So if you were on Pluto, you could actually see red snow falling on the ground. And all this started in terms of a line of reasoning from eclipses, studying Pluto, determining it had an atmosphere. When we look at it now in extended computer extended analysis, stretching the color table, where those dark areas are, that's where the tholins are. That's where the heavy concentration of tholins are. And so indeed, Pluto is so dynamic, we really were surprised. I don't think there were any scientists on the team that had any inkling of how exciting Pluto was going to be. But there's a new story I want to tell about New Horizons, because it's now been targeted to a new Kuiper Belt object. That object is called MU69. This is an object that's much further than Pluto. It's another 8 or 10 astronomical units away. You know, New Horizons has had a small course trajectory, and off it goes. Now, we found that object with Hubble. And Hubble did a fabulous job, you know, looking for Kuiper Belt objects that we could get to. This is the one that was the most promising, and we targeted it. Its visual magnitude is what, if you were an astronomer, this would be impressive because it's magnitude 27. You know, we have no telescopes on Earth that's going to see this thing. You know, it really requires the Hubble to find it. The estimated diameter, based on what we think these objects are like and understanding their reflectivity, therefore getting an idea based on the amount of light that we receive, how big they are, because we really don't know, but this would be the model, is somewhere between 20 and 40 kilometers. And so this is a much smaller object than the 2,000 kilometer Pluto. This is a building block of Pluto. If we want to know how these objects get together and create Plutos, we want to look at these building blocks, and this is just absolutely the perfect one. It's relatively dark, and it's more red than Pluto on top of that. So what do we need to know? This object, when we fly by it, is going to be more than 5.5 hours away, one-way light time, okay? And in a matter of 10 or 12 hours, we're going to be flying by it. We have to know exactly where it's at because we have to have everything automated on board. Turn the camera and take your images, and it better be there. If it's over here, we missed it, all right? And that analysis is going to tell us how much we can tolerate, and it's got to be in the frame somewhere, okay? And therefore, how far away do we need to be based on the uncertainty of knowing exactly where it's at. We do not know where this object is at. We got to figure out a way to really determine where it's at. We don't know where it's at because we haven't watched it orbit the sun. We don't know its orbital period. If we knew its orbital period, we then could begin the calculations of where it's at. We might be several thousand kilometers off on where we think it's at. So how are we going to figure that out? Through an occultation. We found out that this summer, this object, MU69, passes in front of a star. Not once, but 3 different stars, one right after the other. This was an occurrence not to be missed. Now, as you see, here they are, June 3rd, July 10th, and July 17th. These are the tracks where the shadow is going to sweep across the Earth. Now, it's not going to be the huge shadow that we got like Pluto, which is the size of New Zealand, crossing here. This thing's going to be, maybe 100 kilometers in size or less as it sweeps across the Earth, going at 53,000 miles per hour, giving us an opportunity to only observe it from a telescope in a matter of seconds. Okay? So we have to be at the right place, at the right time, looking at this star. Okay? And these 3 stars, 3 different stars, what we found out, of course, is the first example is, well, we can put some telescopes in South America, and we can put some in South Africa. We did that, and we got those observations. Very disappointing. It's almost like we missed it. Now, missing it is also okay, because we're actually interested in, is there debris around there? Anything that can inform us. But we need to go back and try it again. On the 10th, only SOFIA could do this one. Only SOFIA could do this one. And it made its observations, and in a way, it seemed to be a little disappointing also. It's very hard to see if there was an indication of that. And then we went down on the 17th of July in Patagonia. We arrayed 24 telescopes along the highway. The Patagonians came out. They closed the road. The truckers blocked the wind. It was unbelievable to try to get this occultation from these telescopes. And here's one of the observations. And as you see, the star in the center winks at you. And that's because MU69 moved in front of it. This was perhaps the most difficult occultation we have ever attempted. But of course it was necessary because the occultation tells us about its size, tells us about its location, tells us if there's a debris field. Now that we know exactly where it's at, we can go back and take the other sets of data and bring it together and get even more observations and more understanding of this object. It turns out 5 of the telescopes saw it. So here's an example of some of the data. It looks pretty ratty, and then all of a sudden, bam, there it goes. It's about 1.5 seconds to 2 seconds. We got 5 of those. So now let's do the modeling. We can take the telescopes and exactly when they made those observations and map them to the sky and then create a model. And so here was our first attempt at the model, you know. So, hey, this might be an elongated object. That was one of the first elements in the thinking. But then when we brought in the other data and started to look at it more closely, it turns out this is a better model. And that means this may not be one object, but 2. And so it's very typical of the Kuiper Belt. This is a region of these small bodies that are well beyond Pluto. There's thousands of them, and about 30% of those, when we can resolve them, do indeed indicate they're binaries. So this is going to be an incredibly exciting encounter. July 1st, New Horizons is going to fly by this object, and we now have a better idea where it's at, and we know it's going to be exciting and potentially 2 objects to look at in detail. Are they the same? Are they different? What are their characteristics? That's what we will find out with New Horizons. Now, and we did that this year. Another one of the huge opportunities that studying shadows enabled us to do some really important science that's actually mission enabling, and we pulled that off this year. I want to talk about eclipses in other solar systems. Okay? So what happens is an object passing in front of the sun. You know, for us, it was the moon, but it covered everything. And as you can see in this illustration, smaller objects, like planets passing in front of stars, dim the light of the star. The bigger the object, the more is dimmed, more light is taken away that you see. And so over time, you get an intensity that drops. For something the size of the Earth, it's about 0.1% in drop of the starlight. For something the size of Jupiter, it's about 1%. And so, it's far easier for us to find the larger objects using this technique. But we have a tremendous telescope designed to do these kind of occultations, and it's called Kepler. And Kepler's been looking and staring at a patch of sky for several years, and then it's moved to different areas and made more and more observations. And all it's designed to do is just measure the light from the stars that enter its telescope and keep measuring all the time, second after second after second after second, and then allows us to put together that light curve and look at that. That light curve tells us about its size. The length of time tells us about its orbit. Is it close to the star? Is it further away from the star? And so we can put it on a plot like this. And the brand new ones over this last year or so are arrayed across in new dots. And the blue ones are ones that we've been accumulating now for the last several years. And what you see here is relative size. You know, there's the Earth. So if you've got bodies the Earth size and below, you know, so the Earth is our largest terrestrial planet. So below that line would be things like Mars. Even Venus is slightly smaller than the Earth. Certainly Mercury. Mercury would be really hard to find, but we're getting down to that low. But then there's this other region. This region, you know, our next big body in our solar system is Neptune, but you can look at all these bodies that are found that are between Earth size and Neptune size. Okay? And they're all over the place. We call these super Earths. And the more we study them, the more we recognize that they are compositionally very special. Now, Kepler data that I showed you there can be translated in another way, and that is indeed in terms of that other dimension, which is size. So this is where the excursion of the light from each of these transits that are occurring tells us about its size. And when we normalize everything, here is the distribution. And you can see Mars-like objects, or not very many of those. Earth size, that's reasonable, but there are bodies in other solar systems for which the more numerous planets are super-Earths or mini-Neptunes, okay? Those are planets we don't have in our solar system, and yet they seem to be the most populous planet around other stars. You know, we thought maybe, what about big Jupiters? Why isn't Jupiter, you know, everywhere? And as you can see, Jupiter-sized planets are about as common as Earth-sized planets. It's really, really exciting then for us to begin using that to then do other analysis and kind of look at, you know, what's the density of these bodies, these super-Earths. And we're seeing a classification for which the ability to get a body that's a rocky planet that is at a certain size, but a different density than what we're typically used to, requires that we add an enormous amount of water. And so we believe there are a number of these planets that are super-Earths that are ocean-dominated. Also, we believe we can easily see in the data set super-Earths that are largely rocky. There may be some limit to this size. You know, some of the thinking is that when planets get to be 10 times or 15 times the mass of the Earth, they're big enough to accumulate then more gas in their early formation, that they actually are more like gas giants. And what may be on the inside of gas giants are several Earth mass bodies. So that's really exciting. Now, this year, another set of observations came in. These are transit observations from a spacecraft called Spitzer. And as you can see, there's the excursions, and they're very different, and this is why they're labeled A, B, C, D, and this is what the model tells us must be happening, as you can see in the upper panel. And we observed this system for a number of days. This happened this year. Okay? This was really a tremendously exciting set of discoveries, because from this data, we can tell a lot about these planets. And here's what we found out. This system is called TRAPPIST-1. It's a dwarf star, a small dwarf star, very different than our sun, not very luminous, but it's 39 light years away. It is around the corner. Okay, that sounds like a long distance, but, you know, talking to astronomers, you know, it's like our local neighborhood. Now, what's really great about this is indeed there are several of these planets in what we would call the habitable zone, a region for which the light from the star is such that on these bodies, water could exist in three forms. It's not too hot, where it would only be vapor. It's not too cold, where it would only be ice. But in this particular area, in the habitable zone, you could have water, vapor, and the solid, ice. And that's why we call it the habitable zone. So in February, an announcement came out that we found 7 terrestrial-sized bodies. These are all really big bodies. They're Earth-sized and slightly smaller. And generated an enormous amount of excitement. Well, we've studied this system a little more, and that's what eclipses do. It draws our attention to these and allows us to then take a really good look at them and study them. And we found out a couple different things. This dwarf star is really active. It has huge coronal mass ejections, a significant solar wind, a lot of flares, and is hammering these planets. Okay? Not only that, because this star is also much smaller in mass than our own sun, you know, maybe 100 or 120 Jupiter masses, okay, in size, in terms of mass rather. These bodies are all very close to the star, and therefore, like the Galilean moons, as you see in the upper panel, Jupiter and Io, Europa, Ganymede, and Callisto, those are all tidally locked, just like our moon, because they're close to the planet. then these planets appear to be tidally locked to the star. So although they're in the habitable zone, it's tough for us to think about how habitable they might be because they're tidally locked, meaning one face always points to the sun, okay? And they're being hammered by the solar wind. So extreme, it's far different, far more extensive than our own sun does. And as you can see, it's a much smaller system when you compare it to our own. All that could fit inside the orbit of Mercury. And Mercury is nearly tidally locked. But here's the really great discovery. Okay? This star, 39 light years away, when it collapsed and was created, it also had material to create 7 terrestrial planets. That tells us our area of the galaxy is full of planet-making material. That tells us that we have a better chance of finding habitable planets closer to our star than perhaps we thought in the past. And that's done from understanding and following the trail that eclipses lead us. What can follow up TRAPPIST and other nearby planets, of course, is JWST. JWST has been down in the big chamber here at JSC, just came out of that. It's on its way to being completed and it'll be launched in early 2019. And so it's a tremendous telescope that will allow us to follow up on a lot of these discoveries. So what's the next step in planetary analysis? It's really all about going after these planets and looking at their atmosphere. So how do we do that? Here are our 3 planets, Mars, Earth, and Venus. You can see, you get an indication of what is in the atmosphere. Of course, the carbon dioxide signature is strong. If you follow down the water in the ozone signature of Earth, you can really get a very rich spectrum that indicates the potential for life from making atmospheric measurements like our own Earth. And so how are we going to approach that? Well, we're going to look for these atmospheres. And to do that, we're going to talk about shadows. And here's a Venus transit, June the 5th, 2012. For those that may have observed it, Venus crossed the surface of the sun. And what we saw, this little ring of light, is the atmosphere. Once again, just like Pluto, that lights up the atmosphere with that sunlight, just like some of the things that we saw with Cassini. This transit technique was first used in 1761 by an astronomer. I believe he was a Polish astronomer, and not many scientists saw this transit. 176 people, but indeed he was able to see an atmosphere of a planet for the very first time. We thought these were only rocky bodies, and now we're seeing atmospheres, and that's been known now for several hundred years. The next step is to block the light of the stars and look for the planets and look at their atmospheres, which will be illuminated by the light from those stars. And that indeed is our next step, and it will revolutionize looking for potentially Earth-like planets in the future, and it will be done in the shade of the stars. Thank you very much.
Great, well, thank you very much. And we have time for some questions. You may have to speak up. I'm going to see if I can identify a working microphone. But if anyone...
I can repeat them.
Yeah, actually, if you can repeat the questions, that would be great. Yeah, go ahead, right there.
Dr. Frank, can you talk about the Parker mission and what you're doing to prepare for that?
Yeah, so there's a mission called Parker Solar Probe. And the question was, what is that all about? It's actually a solar probe. It's actually a mission to the sun. Now, when we look at the sun and we see this extensive corona, we know that a lot of the upper atmosphere of the sun is trapped on these magnetic field lines. But yet, as you move further back, you actually feel the wind of the sun. The sun constantly outgasses in all directions. So how do you go from an area where most of that hot gas is trapped in the magnetic field to an area where there's gases that are flowing away from the sun in all directions? And that's what Solar Parker probe is going to probe. It's going to fly, we'll have several gravity assists around our Venus, as an example, as it gets to really close to the sun. We'll get to 10 solar radii. And that's an area where we believe this magnetic field structure changes into a radial solar wind structure and facilitates the outgassing that we see, and we call that the solar wind. So we're really going to go to an area that's incredibly hot. So this is a whole variety of new technologies that are being developed to be able to do that, and it's doing really well. It's on track to be launched in another year or so. A couple years, actually. Yes?
This last eclipse, which my wife and I saw in Princeton, Kentucky, I haven't done didn't check out the story yet. We saw the one in Guadalajara also in 1991. It seemed to, I don't know, that's why I'm asking you, was more of the sun blocked out in the one in Guadalajara than the one we just got to see?
Yeah, good question. So the question is, this gentleman has seen a number of eclipses, and this one may have blocked out more sun than the other. And it turns out it didn't. It may be small variations, but the large differences you may see is dependent upon where the sun is in the solar cycle. So during the time when the sun has a few sunspots, the corona is much reduced. And during the time there's a lot of sunspots, it's much more extensive. So that could give the impression that you're looking at a huge sun near solar maximum and a smaller sun during solar minimum, and that's an optical illusion. It's really all about the extent of the corona.
Yeah, but I mean, the moon also is a different distance.
The moon is indeed at different distances.
1991, it seems to me like it was dark. I mean, is there any truth to that? Was the moon closer to the Earth in 1991 than it was this year?
So I'd have to, okay, so the question is, indeed, the moon is in an elliptical orbit, and so sometimes it's closer to the Earth than at other times. And when you compare them, we'd have to look and see which one is closer to the Earth. So what happens when it's closer to the Earth is indeed you have a bigger range, a bigger distance where you could view totality. And indeed it eclipses a little bit of the lower corona, but it's still negligible in terms of the difference between that and what you really see, which is the corona. Yes, sir.
You mentioned accident on Cassini crashing into the moons of Titan, or excuse me, the moons of Saturn. But didn't the Huygens probe crash into Titan?
Yeah, so we dropped the Huygens probe,
Yeah.
but that went through a whole variety of processes to be cleaned to be able to do that. So we knew what may be there. There was some indication, although we hadn't seen the lakes at all when the Voyagers flew by, but seemed to be some indication there might be a significant amount of methane and maybe liquid methane based on the temperature that we thought it was at. And so with that in mind, you have to design your mission such that it can handle those kind of extremes and be mindful of not taking a huge amount of human bioburden on each of these missions as you go doing it.
Thank you.
And there's another question over here? Yes, sir.
I was just going to mention that when my youngest son was born, which he's 25 years old, there was an angular eclipse.
Mm-hmm.
That's really a situation where the moon is more distant.
Correct.
And so an angular.
Yeah. So indeed, there are times where the sun is further, and that's an what we call an annular eclipse. And that's when the moon doesn't completely cover the entire surface. That means the shadow actually ends before it actually touches the ground. But in that case, we were talking about, is it bigger rather than smaller? Is the moon bigger rather than smaller? So we were talking about the other end.
And if I maybe one more question. The last mission that you mentioned, I believe it was called Starshade.
Yes.
Can you explain how that works? Is it actually placing an object at some distance to form an eclipse, an artificial?
Yep, that's, as you see, a star shade is really about blocking that star's light. And based on the modeling, what has to happen is not only a disk, but these funny little fans that stick up all around it eliminates stray light that does occur. And it has to be a significant distance away from the spacecraft itself. And as you can see in this example, separation distance, 30,000 to 50,000 kilometers. I mean, that's enormous. So these two spacecraft, literally the Starshade and the telescope itself, have to operate independently and then yet line up to be able to block a star's light out. And then once you see that, then have enough intensity lighting up a planet's atmosphere. The light, reflected light from the planet, is 1 billion times typically less than the star itself. So you got to get rid of the starlight, and you got to have a big enough telescope where you can actually see the light from the planet. So this is really a challenging mission, but it is indeed another big step for us to be able to then look at the atmosphere and then make comparisons between that and the atmospheres of our own planets in our own solar system, so that we can understand if they're habitable or not. Yeah. Yes, sir? And we'll go over here.
Looking at TRAPPIST and the occultation of that star by those multiple planets, and looking at the dip in the light intensity of the star as the transit occurs, that gives you certain assumptions about the size and mass of the planet that we see for TRAPPIST. But doesn't that assume that transit is occurring across the equatorial plane of the star? How do we know that solar system is not tilted a bit, such that the transits happen, at the lower edge, and so that would completely throw off the size and mass estimates for the planets? What do you do about that?
Yeah. So indeed, every transit that we look at, we have to determine the plane of the planets. Okay? And so they're going to come in a variety of planes. And in fact, there are 30% of the stars that we see that may have planets in it. We'll never see them because their orbit plane may be perpendicular to our observation, never transit. So there's a variety of calculations that are done based on the transiting and multiple observations of the transiting that actually can infer what that inclination is. And it can range all over the place, just so long as those planets cross the disk. And so that indeed affects the size and distance estimates based on those occultations. So all that has to be taken into account to get an accurate size. For mass, you have to go back and verify it with other telescopes to determine how the star may wobble as it moves through space based on the mass of the planets that are tugging and pulling it as they orbit it. And that can be done through what's called a radial velocity measurement. And you can see the light from the star shifting a little bit based on its motion. And then that gives it away in terms of the fact that it's wobbling based on the planets, and then you can calculate their mass. So that's what you have to do to follow up on the eclipses. Yes, sir.
For the balloon experiment you mentioned during eclipses, or during eclipse, why did that need to be, maybe I missed it, but why did that need to be during eclipse, not just at night?
They were launching 57 balloons and got the FAA approval to do it. And it was a ride of an opportunity. It was a ride of a lifetime to get 37 balloons outfitted. And then it also enabled us to engage a whole variety of student population and not only learn about the experiment, but be able to deploy it and follow the procedures of hunting the balloon down and recovering it, and then recording, whether some of these one ended up in the cow pot. So you can't use that one, and then others were dragged on the ground, and so whether the experiment was compromised or not. So instead of the full 30-some, we got about 26 or 27 of them.
The point of being your eclipse was because you get more people to do it?
Well, it was a rite of an opportunity. So we used the balloons because it was a rite of an opportunity, and it enabled us to get to a location where we had a Mars analog. And we could do a whole bunch of them, which would do nothing but improve our statistics. So it's not like a single ride where everything's bet on it. We had a raid across the country.
But I guess would that have worked just at night?
Would that have worked at night?
So during eclipse, was there something special about it?
No. And the reason why is at night, the ultraviolet light would be blocked. And we believe the ultraviolet light is a potential killer for these microbes.
The ultraviolet scatters.
Yeah. So we want to do it during the day. And then we want to be able to get it up to an altitude above the ozone so that the ultraviolet light would indeed be one of those major parameters that we look at. So when we bring those coupons back, we have a control and we see the mortality rate, and then we get an estimate based on its exposure and its path. So we also can get its path, and then we know how long and what the trajectory is. And as you can see, there's all kinds of variations in that. Some were up 1 hour, some were up more than that, 2 hours and more. And so then that also adds into the statistics of it. So it's a great opportunity. It's a rite of an opportunity that allows us to get an array of measurements that all in the same context. And that's very important. And that's being analyzed right now.
Any other questions? Yeah.
I can see a way that you could get more eclipse data from the moon if you say we're going to at an equilateral point in the Earth-Moon system, but would it be worth it?
So the architecture of why and how we get eclipse really starts with understanding the plane of the moon. And the plane of the moon is actually cocked a few degrees. Right. And so then as we move around that sun, then that plane allows it to change orientation relative to the sun. And you've got to be at the right place, at one of these nodes that allow then the sunlight to shine on the Earth. And then as the Earth spins, that's why you have different locations for the eclipse. But indeed, every new moon, if you could see the moon in the middle of the day, passes above the sun or below the sun, because that's where it's at in its slightly tipped orbit.
Well, say if you had a triangle, and there are all the ecliptic planes somewhere, as the moon would pass through that, then there would be opportunities that you would get the eclipse, and then you could maintain some orbital adjustments if it was a spacecraft.
So you're talking, okay, so your question may be relative to a spacecraft using the moon for eclipses. Well, indeed, a spacecraft that observe the sun see the moon pass in front of it all the time, okay? But it's, I don't believe in all the years that we've been up there, we've actually caught the right example where the moon covers the sun from a spacecraft perspective and created an eclipse.
It would be an equilateral triangle.
Yeah.
The same distance as the Earth's surface.
Yeah, I don't know of any observation we've taken from any of our solar observers that do that. Yes, sir.
I'm going to get back to my recent Kentucky experience. I wish I'd done my homework in advance because I forgot all about being able to see Mercury.
Yeah.
And I wish I had known where to look.
Yeah.
I'm sure I saw it, but I don't know.
It may not be Mercury, it may be Venus. Yeah.
Unless it would have been a bummer. And Mercury were like damn near in line with the
Could have been behind it. Yeah.
Do you know where it was?
Yeah. So relative to the planets, during the eclipse, we know where the planets are. So during the eclipse, the last one in particular, Venus was off to the right.
Yes, I remember that.
Okay.
Yeah, but
That just popped right out. That was really obvious. Mercury was a little harder to see. It was off to the left. And Mars was a little further away from that.
And was Mercury like, far to the, if it were like really far, in its orbit cycle,
Yeah.
was it like pretty far away at the time?
That's a good question.
Because if it were really, really close.
No, it wasn't really close to the sun. Yeah, it wasn't really close to the sun. It was Mercury was indeed well away from the sun that you could have seen it if you knew where to look. You needed to be in totality. You needed to be in the area of totality. I was. This was actually my first total eclipse, and I was in Idaho. I was in Idaho Falls, and it was one of the NASA broadcast places. NASA broadcasted from like 10 locations along the eclipse path. And so they would go from place to place to place during totality, and we would report on what we saw and what was going on. And I was pretty excited because it was first one. So it got really dark. It was just fantastic. And Venus popped out. It was great. And then the street lights turned on. Had I really thought about that, I would not have been anywhere near a town. I would have been out in the country somewhere. But the hazards of your first eclipse.
All right. Well, we haven't yet fed our speaker, and he's been working very hard all day. So I'd like to thank Dr. Green again.
My pleasure. My pleasure. Thank you very much. Thank you very much.
And thank you all very much for coming, and look out on the mailing list for the next Spaceport Frontier lecture, which I no doubt will be in the very near future. Thank you very much.